Welcome back to Basic Mathematics. In this video, we're going to be taking a look at ratios and rates. You can think of ratios as kind of a generalization of the idea of fractions. They allow us to work with fractions while also including decimal numbers and fractions themselves in the numerator and denominator instead of sticking to whole numbers. Sometimes you can get away with things with ratios and rates, like not reducing a fraction. Sometimes you will still have to reduce them the same way you reduce fractions, depending on context. As we're getting into starting this discussion of ratios and rates, one thing that I want to mention is that unfortunately the software that we use, the MyMathLab system, doesn't have a good way for me to filter out questions that have some very annoying decimal numbers. In the videos on decimal numbers, I'll be talking through the kinds of problems I expect you to be able to work through by hand and the kinds of problems that are just too time-consuming and tedious to be worth thinking about. I encourage you to try to practice the problems that involve decimal numbers, working through the arithmetic by hand. But in those particular instances, if the numbers get too convoluted and you have to reach for a calculator, don't feel too bad about it. On the exams in this course, I can assure you that even when decimal numbers appear, you're not going to see anything that is too outlandish, and you are expected to complete the exams in this course without the use of a calculator. That said, let me get my head out of the way and let's get into the content. Formally, we can say that a ratio is the quotient of two quantities. Quotient, you should remember, is the result of doing division. And when we say quantities, your brain probably jumps to the idea of numbers, but technically, I mean something slightly different. I mean measured values. Once again, here now the definition starts to feel more restrictive than I mean to. When I say quantities, I don't want to just talk about numbers. I want to talk about numbers that have some meaning to the world. And when we call that sort of a meaning to the world a measurement, when you hear the word measurement, you probably imagine someone grabbing a ruler and holding it up to an object to determine its length, width, or height. You might think of someone using a balance or scale to find the mass or weight of something. You might think of the various tools that exist to measure a volume of an object. And while all of those things certainly are measurements, measurements also include things like counting. For example, one thing that we track in our incoming classes here at the college is the gender ratio. The number of men who register for classes divided by the number of women. When I'm in a classroom teaching this lesson, I will generally do a head count at this point to calculate the gender ratio of my particular class. Through the internet, I'm not able to take a quick look around, but in one of the classes I taught recently, I had 17 men and 12 women for 29 total students in the class. And since a ratio is the result of doing division, we can certainly write the ratio using fraction notation like this. But when we talk about ratios, there are a couple of other notations that are pretty common. The colon notation, 17 to 12 is how this is read, is a fairly common way of dealing with ratios. Every now and then, I'll actually see that written out in words, 17 to 12. Just like with fractions, when you're dealing with ratios, there are going to be times when it is worth taking the time to reduce the ratio. The ratio 17 to 12 does not reduce, but if we had a slightly different ratio here, let's take a look at the ratio of 24 to 18. I can think of this ratio as the fraction 24 over 18. And you may notice offhand that 24 is 4 times 6, 18 is 3 times 6. The factors of 6 cancel each other out. So 24 over 18 reduces to 4 over 3. Now that we have reduced the fraction, we can come back to the ratio notation and say that the ratio of 24 to 18 is the same thing as the ratio of 4 to 3. I said in the opening that one of the nice things about ratios is that they allow us to generalize the idea of fractions to look at fractions that contain decimals or fractions themselves. So if I have the ratio of 4.7 to 3.6, I can write that as the fraction 4.7 over 3.6. And if I want to clean this up, I can in fact multiply to find a common denominator that does not have a decimal in it. In this particular case, if I multiply 4.7 by 10, I get 47. And if I multiply 3.6 by 10, I get 36. Right? You can't reduce this particular one any further, but that does give us a nice way of taking some ratios that contain fraction or contain decimals and turn it into something that does not contain decimals. Same sort of thing will work with fractions and mixed numbers. Consider the ratio of 3 5/8 to 4 2/3. Before I do anything else, it turns out that it's very convenient working with ratios to take our mixed numbers and rewrite them as improper fractions. As we saw previously, most of mathematics, most of arithmetic is easier with improper fractions than it is with mixed numbers. So 8 times 3 is 24, 24 plus 5 is 29. 3 times 4 is 12, 12 plus 2 is 14. So I've got 29 over 8 to 14 over 3. All right. So we'll write that as a fraction, 29 over 8 over 14 over 3. And if I multiply top and bottom of this fraction by 8, the denominator is going to be a bit more of a mess, but in the numerator, the 8s are going to cancel each other out. Let's see, 14 times 8 is 112. That's still over 3. But now I can multiply numerator and denominator of the big fraction by 3 to get rid of that denominator. 29 times 3 is 87. So the ratio of 3 5/8 to 4 2/3 is the same thing as the ratio of 87 to 112. That's really all there is to the idea of ratios. Our next definition, a rate, is the quotient of two different quantities. Once again, at first glance, this definition kind of seems silly. Of course, when we're dividing numbers, we are generally going to be looking at two different numbers, right? Counting the number of men, counting the number of women. Another common ratio is an aspect ratio, the width of an object divided by the length of the object. When I say rate, or when I say different here, when I'm talking about a rate, what I'm talking about specifically is a situation where I have two different kinds of measurement. If I'm looking at the gender ratio, when I want the number of men, I count humans. When I want the number of women, I also count humans. It's the same kind of measurement, measuring a slightly different item. Likewise, an aspect ratio, measuring the length of an object, measuring the height of an object, is the same kind of measurement. It's just measuring two different things. A rate, we're going to be looking at, say, a measurement of a distance in miles compared to a measurement of a time, say, in minutes. And here's where I said the decimal arithmetic can get to be kind of nasty. If a problem like this showed up in my math lab, I wouldn't object to you grabbing a calculator. But numbers like this will not show up on the exams where you are not permitted to use a calculator. But I can take 47, I can divide by 60, I can get a decimal number that looks something kind of like 0.783. And when I have miles divided by minutes, to talk about that in units, we use the word per. When we've performed the division like this, we end up with a quantity that's known as a unit rate. That's the thing that you see most often when you see the word rate. And you can identify a unit rate whenever you see the word per in the measurements used. Miles per minute is not a very common unit rate. But we can, of course, also look at miles per hour or feet per second, very useful measurements for a rate of speed. You can also look at the rate at which you are charged for goods. Dollars per gallon or per pound or per ounce. Are common ideas there. If you spend a little bit of time thinking about it, I'm sure that you will be able to come up with dozens of other places in your everyday life where you talk about something and you have a unit given with the word per in it. Anytime you have that, you're talking about a unit rate. Unit rates are really useful, really convenient problem-solving tools. For example, if you travel at 35 miles per hour for 2.5 hours, it turns out that it's really easy to calculate how far you went. Because 35 miles per hour is 35 miles divided by hour. Well, divided by hour is a little bit weird. We can always throw in a 1 without changing anything. And if you multiply that times 2.5 hours, throw that over 1 so it looks like a fraction. Notice that the hours will cancel each other out. Dividing by 1 doesn't really do anything. And you have 35 times 2.5 in miles. I can go off to the side and multiply 35 times 2.5. And I see that if you are driving at 35 miles per hour for 2.5 hours, you will have traveled a total distance of 85.5 miles. Another place that unit rates are incredibly useful is looking at comparing costs. Consider the situation where you can purchase an 18-ounce bottle of whatever it is you're buying in a bottle for $4.32, or you can purchase the 25-ounce bottle for $5.75. You can work through and find the unit rate as a nice way of determining which of these two bottles is going to give you the better value, which one is going to be the better purchase. Conventional wisdom tells you that the largest bottle is always the best value. And while that is often true, it's not always true. So understanding how to do this calculation can certainly be important. If we compare cost per ounce, let's see, 18 will fit into 43 twice. 2 times 18 is 36. Subtract that off, and we have 7. Drop down to 2. 18 fits into 72. I think that fits 4 times exactly. 4 times 8 is 32. 4 times 1 is 4, plus 3 is 7. Yep, that works out exactly. So the 18-ounce bottle is being sold at about 24 cents per ounce. Doing the same sort of calculation with the other bottle, uh, 25 fits into 57 twice. 2 times 25 is 50. Subtract that off, you get 7. Drop down the 5. 25 goes into 75 3 times. And in this particular case, we see that the 25-ounce bottle is selling at 23 cents per ounce. You save 1 penny per ounce by buying the larger bottle, which doesn't seem like a lot at first, and might not be a lot depending on how much of this particular product you're buying. If you use 20 ounces of this product every week, well, then you're saving 20 cents every week for 52 weeks in a year is going to be a difference of about $10, a little bit more than, over the course of an entire year. These kinds of savings certainly can add up and be useful, and this is why I carry a calculator around with me whenever I'm at a store. Right. So that's about it for the idea of ratios and rates. In the next video, I'm going to introduce you to the idea of proportions, which is the most powerful problem-solving tool we have working with ratios and rates. And, excuse me, honestly, quite probably the most powerful problem-solving tool we have in all of mathematics is the idea of proportions. Excuse me. Take a look at the practice problems in the MML activity. Once you're comfortable with those, I'll see you in the next video.